So presenter is Carrie Nagoda, and then she did this work with Lillian Bousset. We talked about Lillian yesterday. They both work for the San Diego Regional Water Quality Control Board, and I think I'm just going to bring you up.
Okay, thanks. And this is already on. Do I need to turn this on, or it's good? Hi, I'm Carrie Nagoda, and I've been working with the San Diego Water Board for about 1 year now, where I've had the privilege of working with Lillian Bousset on many of her wonderful projects that she has going on all at the same time. And I want to thank Jim for fitting us in at the last minute, but I'll try to keep it quick since we're already over. So today I'm going to talk to you about how we discovered cyanotoxins in many different water body types throughout Southern California. And I just wanted to mention some of the other contributors to our work, which includes Lillian, of course, Chad from the Water Board as well, and some folks from SWRCB, including Betty, Meredith, Eric, Martha, and then the Kudela Lab at UC Santa Cruz. So my presentation, I'll do a brief introduction and then get into the water body types where we've seen the cyanotoxins, talk about the data sources, go over some of our methods and results, and then I'll give you some take-home messages and talk about our next steps. So why are we concerned about cyanotoxins? I believe Kim covered that really well, but I just wanted to point out again the third bullet, the fact that the bloom distributions are expanding worldwide, they're lasting longer, and they are producing more toxins. That seems to be the trend. So I think that's why we need to really think about those more closely. And then also the last bullet, the fact that there aren't any cyanotoxin monitoring programs within our region or even statewide in California. And another important issue to consider with cyanotoxins is the fact that they do have far-reaching effects. And I know Kim also spoke about this study briefly, but I think many of you are probably aware of the sea otter deaths that happened in Monterey Bay. And it was pretty clearly linked to microcystin that started in Pinto Lake, made its way downstream, and was bioaccumulated in some marine bivalves that were then eaten by the sea otters and caused the toxicity and the deaths in them. So we had a unique opportunity to piggyback onto quite a few studies to gather a lot of data for this work. And some of the data was collected through the Stormwater Monitoring Coalition, or the SMC, some special studies at SWRCB. And most of these focused on microcystins, which are the most common cyanotoxins, but we did have the ability to gather some data on saxitoxins, lingbiatoxin, anatoxin, cylindrospermopsin, and nodularin. So basically with these studies, what happened when the field crews were out, we would say, can you grab an extra sample that could then be brought back and analyzed for cyanotoxins? So some of the water body types were screened all throughout Southern California, and others were more limited to our region. For Southern California, we were able to look at many different stream sites, and again, that was through the SMC work, and that was a probabilistic study. And we also used a targeted study that was the San Diego Reference Stream Study run by SWRCB. And also we used a probabilistic study to gather information on depressional wetlands, which was a swamp-funded study run through SWRCB, and that looked at the extent and condition of depressional wetlands throughout Southern California. And then in my region, which was my focus mostly this summer, was our work done in lakes and reservoirs and coastal wetlands. So that was more limited to the San Diego region, and it was a targeted study. But the sites were not targeted for the fact that we thought that they would be the worst conditions or have the most cyanobacteria. They were more targeted because of the beneficial uses that would be impacted should we find cyanotoxins there. So we chose lakes that were used for drinking water uses or fishing, recreation. And again, with the coastal wetlands, ones that we knew there would be more people around. So we used two different methods to collect our cyanotoxin data, and the first are grab samples, where you get the particulate component. So that's basically taking a known volume of water and running it through the filter. And then what you can get with that are the toxins that are actually inside of the cyanobacteria cells. And then we also used a continuous method, which used SPAT samplers, and that stands for solid phase adsorption toxin tracking samplers. And so those are these little discs that have resin beads inside of them, and the resin has the ability to absorb toxins, and in this case, it had the ability to absorb microcystin. So these spat samplers stayed in the water for 1 month at a time and gathered the toxins, and then we had those analyzed. So I just wanted to briefly mention why we thought it was important to use both methods, because as you can imagine, when you take grab samples, that's just a one-time spot check, so you could potentially miss some toxic events that are happening. So and this graph just shows when you do have spat deployments, how you can, on the left-hand side, you can completely miss maybe some events that happen with your grab. You get a sample that isn't toxic when you really did have a toxic event. And then on the right, it shows where maybe if you had a continuous deployment device out there where you had maybe higher concentrations, but your grab sample actually brings back a lower concentration, so you don't miss that spike. And a little bit more about the study this summer on the lakes and reservoirs and the estuaries, how we did it. We had 2 different spat deployments, and so we would take our first spat out and leave it in the lake, reservoir, or estuary for 1 month. And so when we took it out, we would take a grab sample, go back after 1 month, retrieve that spat, take another grab sample, and then deploy a second spat, and then go back a 3rd time for a grab sample. And we did this for 9 coastal wetlands and 10 lakes and reservoirs throughout the San Diego region. With our grab samples, we also got some background data, including nutrients and chlorophylls and pigments as well. So what we found, we were anticipating potentially maybe 50% of our sites would get hits with the spat samplers, and that's what we were going to use to trigger whether or not we should send our grab sample, the particulate samples, to the lab to be analyzed, just for funding reasons. But when our results came back with the spat, to our surprise, every single one of our sites had a hit for microcystin in at least 1 time during the study. So you see all of that green. And except for the site that's 3rd from the bottom, at the one reservoir we had, our first spat was missing and the second one was damaged. But other than that, every single site had a microcystin hit. And then I wanted to just point out the very last site on the bottom, the Tijuana River estuary, that the concentration inside that spat, that first spat, was just completely off the charts. And we don't have our filter results yet for this study, but those should be coming in within about a few months. And then just to give a little geographical context, hopefully you can see it, to our data that we collected this summer, and this is just based on the spat sampler results, pretty much 100% hits for microcystin detection. And you can see that it sites all the way from the coast to inland, and it's agricultural areas as well as urban areas. So it's pretty widespread in multiple land uses. And to talk about the studies where we also had some of the data, so the streams, the data was collected in 2011 and 2012. And again, this was a probabilistic study. And for this map right here, you just see results from the filter, so that's the particulate samples. I'm sorry, those are from the benthic algae samples. And you can see that we had microcystin found in 62% of the sites. So again, probabilistic, I mean, we're seeing a lot of hits. This is about 50% you can count on having microcystin in your stream systems in Southern California. And here's a map of the depressional wetlands results. And this is a combination of some of the filter results as well as the spat results. And this, again, was a probabilistically designed study. And you see we get almost half of the time, too. Here we're getting hits for microcystin. And with this study, I believe at least 1 or 2 of these sites per year were actually, the concentrations were above the California action limits. And so here's just a final map showing you a combination of all the different water body types, so you can see how widespread the microcystins are found. So it's depressional wetlands, coastal lagoons, lakes, streams, rivers, estuary. It's found in the plankton, the benthos, and dissolved fractions, and it's across many different land types. So my take-home messages for this presentation are that cyanotoxins have been detected throughout Southern California in a very wide variety of water bodies, And there are multiple types of cyanotoxins. I know I'm mostly focused on microcystin, but they have been detected and sometimes simultaneously with others, including anatoxins, cylindrospermopsin, limbia, and saxitoxins. The cyanotoxins can affect areas far downstream from their biological origin, as shown with the sea otter deaths in Monterey. And that the spat samplers that we use are a great screening tool. They provide continuous monitoring, and they're relatively inexpensive, and they're very reliable. And it's a way to capture ephemeral events that traditional grab samples might miss. So our next steps, once we get all the data in, we'll create a report that includes the streams, depressional wetlands, lakes, reservoirs, and coastal wetlands. In the future, we'd like to continue cyanotoxin monitoring studies beyond this, just first cut screening level approach, and possibly include bioaccumulation. And of course, important is to develop a monitoring program in Southern California and throughout the whole state. So I just wanted to say, I mean, if we went out there and did this screening study and didn't have very many hits, then I think it would be something that we might not need to worry about. But the fact that this was, you know, a first time and we found so many toxic sites, I think it's something that we really need to pay attention to, as echoed by Kim and Dave. So thank you. Let's take questions.
Well, if there's not a pressing question, maybe we can, Carrie, you're going to be around? And is there anyone dying? Oh, there is a dying person.
Where do these things come from? How do they get so widespread? Are they distributed by animals or something, like birds? Or
Where do they come? I mean, I know they grow because of high nutrient levels and they can outcompete other bacteria, but the source, original
just
source
present in
maybe-
all waters, and now they're
Yeah.
taking off?
Yeah.
Well, wait a minute.
Thank you. Yeah, they're ubiquitous. They're very important in the marine phytoplankton. They produce a lot of toxins out there too. They're prevalent in estuaries. They're prevalent in all surface waters, including surface waters where you might not think anything could live. So they're found in some very extreme environments on this planet. Yes, actually, the question was, are they a bacteria or are they not a bacteria? Yeah, they're a true bacterium. They happen to be a photosynthetic bacterium.
Do you know if there's any relationship between these blooms and increasing ozone layer?
Oh, excellent question. I have absolutely no idea. But I will say this much. They are resistant to ionizing radiation, and that was thought to be more of an issue back in the days of early Earth, before we had as many gases in the atmosphere as we have now, and when we didn't have an ozone layer, presumably.
You know, I made a joke about going over.
So in the case of the sea otters, where you've actually determined a source for these microcystins, is there something can be done to reduce that? Was there something done to reduce that?
Well, in the literature, there aren't too many published studies that show you exactly how to remove the problem without actually killing everything in a natural water body. I mentioned copper sulfate and hydrogen peroxide. That's often used, and then you wind up with eventually cyanobacterial blooms that are resistant to all the substances you're using to kill them off, plus you kill everything else. So the limited published data that we had access to indicated that at Pinto Lake, for example, where I have a grant study that's wrapping up right now, researchers looked at different types of treatment technologies. Ozone looked pretty good. The unfortunate thing about ozone is it's tricky, it's energy intensive, and it's dangerous equipment, and scalability may be an issue. Filtration didn't work out very well with sand filters. Basically, you're providing an area for a biofilm to start growing. Some combination of methods might actually work, and there are people in the drinking water treatment end of things who've progressed a lot further than folks like us, if you want to take a look at it in terms of conserving a lake. But their objective is basically drinking water, and if the fish die, that's not a big problem.
Thank you. I think we should move on. Again, if you have more questions, take them to lunch and ask them there. Okay, so the next two presentations are going to be given by people from SWRCB. Now, we've used that acronym before. I just want everyone to understand it's Southern California Coastal Water Research Project. They've been around for a while, emphasizing in marine first, but really, doing a lot of work collaboratively with us. You know, I keep talking about our aquatic bioassessment lab, but they're equal partners in this effort for bio-objectives and bioassessment techniques. Ken Schiff, who's usually here, couldn't make it today, but you were introduced to Eric yesterday. He's going to start the first presentation of the last two in this session. Eric?